Our next presenter is Thomas Gunkel, who is the Market Director Broadcast for Skyline Communications. And he's going to be talking about SDN orchestration. So how do we properly control a network to route our video signals and our audio signals and our data signals across a multi-switch backplane using SDN technology. Welcome, Thomas.
Thanks, Wes. Thanks, everyone. Next 25 minutes, it's about really a use case, a project we have deployed in Italy, an SDN orchestration project, actually, something that went on air end of last year. Customer, we can talk about this, is Rai Way in Italy, which is a service provider, telco, mainly managing TV, also radio, DAB, FM, radio transmission for Rai and local broadcasters. They have their own fiber network, that's important to know. For contribution distribution, they run their own transmission sites, a couple of thousands of those. They also have a DTH facility, and everything is managed by multiple NOCs. The project about 2 years ago when they started, it was called the IPMatrix project. What was it about? It was about to replace existing SDI infrastructure. From the point where the signal leaves Rai and other facilities to the head end, from the head end out again to the distribution sites. IP transport of video, audio, data signals across multiple sites, mainly via dark fiber, DWDM. Several ones, a couple of them in Rome, also some in Milan, in Turin. It's really across Italy. It's a geo-redundant data center as well, where we have deployed our data miner platform, the SDN orchestration platform, in a way that it had to run 24/7, even if one site goes completely down. Same goes for the operations. They can operate everything either from Rome or Milan, and certainly no single point of failure architecture had to be implemented there. Here a bit more details. We have about 100 to 150 channels on air nowadays. That's just an example for one channel, Rai 1 in that case, where we have a main and protect SDI signal, goes into an IP encoder from SDI to IP, uncompressed, or 2022-6 or 2110. So in fact, this is a 2022-7 network as well. So we have a minimum of 4 copies for each and every channel. Then we leave the first facility, will be transferred via dark fiber into the head ends. There we have again spine leaf networks, local ones. Different types of networks need to be managed in there, different types of head ends. We had some head ends, they were still SDI based, so we converted back from IP to SDI, encoded, goes into the multiplex. Then there were head ends a bit more modern, they were purely IP based, so we did some netting there. Again, the encoder and multiplex part. Then it goes into another spine leaf, leaves the site again, will be transferred via WAN, comes back into spine leaf architectures, will be netted again, goes to another facility, goes to the distribution sites, will be netted, change over units, and then distributed to different end devices via MPLS networks, Nimbra devices, etc., or complete Nimbra networks. So quite a complex setup for a single channel. The converged red and blue network, as you can see here, was realized partially with Arista and partially with Cisco. Once more, the spine leaf architecture here on the local facilities. This was all non-blocking, and all the WAN connectivity, those were obviously blocking connections. How did we start the project? We put a big focus on the automated onboarding and the secure onboarding. We have a tool set deployed, what we call infrastructure discovery and provisioning. First thing we did is to automatically discover all the network devices and media edge devices in the network by scanning the network, or as an alternative by interfacing to third-party databases. One of them was NMOS ISO4. Then second, we had to provision all the detected devices in the data miner platform, apply the right configuration, and also apply software updates and firmware upgrades if necessary. to have an automated, a fully automated process, a zero-touch provisioning process, as we call it, up to the point that you have a trusted device that is properly configured to start using it the first time. How are we doing that under the hood? We are using so-called configuration items, CI types. And there we define the behavior and the properties of each configuration item type. And you see in this list, it's not only the switches like the Arista and Cisco switches, but also the edge devices from Imagine, communications from Magic, from Meinberg, Testry, a couple of more in there. What's also important when you talk about SDN control, we need to learn about the connectivity. This is something we did, again, for Arista and Cisco, using two different protocols. For Arista, we were using LLDP protocols. For Cisco, the Cisco Discovery Protocol. The result is the same. You end up having all the information, how things are connected, including the media edge devices, and we store that in our database. Whenever there is a change, we run the same process again, and we always keep the infrastructure and the topology up to date. As a second option, we provided them a possibility to also import connectivity via an external topology database, because not on every switch we could activate the protocols LLDP or CDP. And some of the information that was in this topology database was also extracted to know exactly in which location those switches are, which room, which rack, etc. Here's just a screenshot of a managed device. That is a Cisco Nexus example, where we have finished the detection of the device. We have added it to the data miner platform. We have applied the right connector, the right driver, as we say. We have applied the base configuration, firmware upgrade, and also alarm and trend templates, because immediately you want to monitor the health state of your devices once you have detected and configured those. Now about connection management. What we had to do, what was most important for Raiway, is to say we want one single user interface that allows us to support any kind of compressed, uncompressed flows on the same UI. We ended up designing what they call a list view, which is just the sources on the left, destinations on the right. Very classic routing application at the end, which you can compare against SDI, because all the operators were used to have SDI for many years, but with filtering capabilities. A couple of thousand sources, destinations, virtual sources in between, where they can easily find their sources, their destinations they need. And with a single click, it's really source, destination, take operation. They make their connection. Important here, it's not like single hop connections, it's the full service setup. What you have seen in the third or fourth slide, the full connection from an uncompressed start up to the compressed destination they do with a single click there. We manage the complexity under the hood. As a result, we also create those flow visuals or visual overviews for every connection we make. We start monitoring that connection. That's something I will show later as well in more detail. And here that connection, just as an example, was a 2022-7 one. We go from SDI into the IP gateway, do some netting, goes into the head end where it will be encoded. That's what they wanted to have with a single click. A couple of more examples on sources, destinations. When we talk about HD streams, we're using 2022-6 point-to-multipoint connections. One source represents then two multicast flows, because they were also using 2022-7. Some others, when we talk about UHD streams, more and more they provide and broadcast via UHD. It's all SMPTE 2110. We have 2110-20, 30, 31, 40. Again, redundant. For the operator, it looks pretty much the same. Single source entry. In this case, we have 10 multicast flows represented by that one. They have 3 audio streams, 1 video stream, and an auxiliary data stream. How do we do that under the hood? We are using so-called virtual signal groups, where we can just combine anything you want. Can be still SDI, can be 2110, can be a mix of everything. It's a layer under the hood. It's a hidden layer to the operator, where we combine any of the logic, any of the streams or connectivity you want to put that together and call it a source. In the compressed world, it looks similar, but there was one big difference. They wanted to have something to route compressed streams from a main, a backup, and a disaster recovery head, and also with a single click. To do that, we had to do an operation where you can collect or select multiple sources, because you want to have the main, the backup, and the protect routed to a single destination. So it's not source destination. Here is multiple sources to a single destination. As a result, you get something like this. Again, a monitored connection. Why did we have to do that? We had to, first of all, set up flows that were completely independent from the other one, so we need to know what belongs together. Then we also had to route those flows into some changeover units. So that belongs together, we call it a single service. You could not route those signals completely independent, otherwise there is a risk that those signals use joint sources, and whenever something goes wrong, that would impact the no single point of failure policy there. What you have seen so far, we call this a full service connect. So with a single cross point, source destination take control, we managed a complete connection, a complete service under the hood. How can you do that? You have to predefine it in one or the other way. We have so-called service templates. You define this up front, and then you provide the simple user interface to the user. What people can also do, because there's always a situation that you say, I have some of those service definitions, but today I want to do something different. We have the very classic single hop connectivity where you only go from one output to the next input. So here you have a couple of hundred sources destinations. Over there, same user interface again, but designed for engineers. They have access to every single source and destination across the complete chain to define new sources and new services, but also to use those to route signals to multi-viewers, to probes, etc. What's important as well, everything is time aware. We can make those connections ad hoc. You can plan them in the future. You can have permanent connections or have connections with an end date. The SDN controller data miner knows about the capacity right now in the network, but also in the future. So they do a lot of operations where they say, in a week or in 2 weeks, we need to reshuffle a couple of multiplexes. We have a new DVB-T2 channel on air. That's all pre-scheduled. That's something they do up front. We can tell them if there is still sufficient capacity in the network, if they have sufficient media edge devices available. How does it work under the hood? A bit more on the what we call a data miner network manager. First thing we do to set up a connection, we detect the input format. If it's SDSDI, HDSDI, or UHD, depending on that, what we detect on the first input device, we configure the sender, set up the right profile. Then you need to calculate, like other SDN controllers as well, a path. We call it the most efficient network path, which is a combination of the shortest path in the network and lowest cost. Customer has assigned cost to each and every network interface, because some of the connections are leased lines and some they own. So obviously they prefer their own fiber and dark fibers across the leased lines. And that combined with device availability, monitoring also comes together with like control. When a device is not available or in plant maintenance, you have to exclude it from the available path or devices. And then together combined with the required and available bandwidth for the scheduled time. If there is no bandwidth available anymore, you need to rerun the Dijkstra algorithm. We use Dijkstra here to see if we find any other alternative. Then we set static multicast routes. There is no IGMP at all. It's all set by the SDN controller via static multicast routes on Bosch, Cisco, and Arista. They run all in what they call passive mode, and then we configure the receiver to set up the complete connection. By the way, setting up the sender and receiver can be based on NMOS, ISO5, but also we support the vendor-specific APIs. In reality, what we have seen for this project rollout, they didn't use ISO5 at the end. Why is that? Products were not ready. The proprietary or vendor-specific APIs just worked better at the time when we have deployed the project. Some more specifics here on the Network manager, we set diverse paths for main, protect, and disaster recovery flows. We route those multicast flows that belong to one source across the same network path. That was a customer decision. They wanted to have it like that, so we have implemented it in this way. We know about device limitations, obviously on the interface bandwidth, but what was also important for them to know about the license bandwidth per device. We have some probes, for example, they have a 40 or 100 gig interface, but they only have a license for 20 or 60 gigabit of probing. So that's something you have to know, not to oversubscribe the bandwidth of the license bandwidth you have in that probe. We do netting, as you have seen, manage changeover units, control multi-viewers, attach those probes, and then everything we do goes together with what we call service-aware monitoring. Next couple of minutes, I want to talk about this a bit. Whenever we set up a connection, we set up also a monitoring layer dynamically. That's both for the multiplexes that leave the head end, but also for all the contribution feeds, which are uncompressed feeds. And one of those lines, here you see the multiplexes, and on the right-hand side down there, you see every single uncompressed connection we have made. So whenever something goes wrong in the multiplex, you see pretty easily on this dashboard already if the root cause is more in the multiplex or if something goes right there, root cause might be in the contribution feed. Then you click on one of those rectangles, you drill down a bit, and you see more. We monitor what we call with a service perspective. So every single connection that belongs, in this case, to RAI1 will be grouped together. There's like 1 input to 4 outputs, the same for the backup source. So 8 connections made. But from a monitoring perspective, we group them all together to see again the root cause when something goes wrong, if your problem is related to the source or more to the destinations. Then you drill down again for more details. You click on one of those rectangles again, and you see the actual single connection from an SDI to IP into the network via netting to the encoder. Most important KPIs will be shown there. And you can go into more details on the network. In this case, we show the Cisco network connectivity, only those interfaces and switches we have calculated the path for, and we monitor against the expected bandwidth versus the bandwidth we can read from each and every interface of those switches to really make sure what we have set up in the network that it's actually there. It's more like a cross-check. So we set up something with our controller, and then we look into the network and crawl through the network to see if everything is still up and running as we want it. Another example here on the UHD stream. Obviously, you need a few more data to monitor. It's not only one stream. For the audio tracks, for the data tracks, you get more KPIs exposed on those visual overviews. And all of those, they are always dynamically created. So when you connect, or when you set up a connection, we create that visual. When you unconnect, disconnect, it's gone again. It's not available anymore. A multiplex, pretty similar. You have this group overview, your main, your protect, and the disaster recovery side. There was one issue on one of those connections. Then you drill down to that one. This is the connection overview where you have 3 outputs of the same content going into the networks, goes into the changeover unit, will be netted, goes then into a ASI converter. And here there was a second leg which had no bandwidth. There was a problem on the SFP by that time, by the way. Then not only connection monitoring, we also monitor the network as such when you're not looking into a single connection, but more from a network perspective. That's a, again, dynamically created visual overview or network topology view between the sites. You have here something in Saxa, goes to Monte Mario in Italy, the spine leaf networks, the spine switches. When something goes wrong, you would see that immediately color-coded in a different color. To see more details, same thing again. You click on one of those rectangles on the other side. Here is the Monte Mario head end. You see the spine leaf network and all the connected end devices. Something I want to talk about just for a minute is virtual sources. What we do whenever we do a single connection from a source to a destination, there are many hops in between. For each and every hop a signal crosses, we create a new virtual source. This is immediately available to the operator. Why is that? When you want to route a signal somewhere in between those multiple hops to a multi-viewer, you can use those as a new virtual source. Same thing, instead of looking into the source destination table here, you can do on these visual overviews to make it really easy for the operator. There's a small little button for multi-point probing. So we activate those buttons, you click on it, and we route the multicast stream to a probe. In that case, that's something from test tree, where we decode audio and video and get the most important metrics through that probe back into the system. Then not only monitoring and basic connection management, we also implemented a few workflows for disaster recovery and maintenance. And one of the use cases they have, every couple of weeks, months, they need to free up a complete headend for maintenance. So every single uncompressed channel or stream that goes into one headend needs to be rerouted to a disaster recovery headend, and all the connections, all the outputs from one headend need to be rerouted again to be taken from the disaster recovery. So that would be a couple of hundred connections to be made, or a couple of thousand streams actually. We implemented some logic for the operator there to say it's a single click. That's really the button they have to hit to route, in this case, one single multiplex coming from one headend to the disaster recovery headend. So a couple of hundred cross points under the hood we do to free up one of those headends for them. What's next? Project has been delivered end of last year. They are live since October 2021. They're adding more channels. Next big step is to also use the very same system for the DAB+ services, audio only. They're constantly adding more UHD channels. Some of the headends will still be refurbished. You have seen some are still in SDI. They will all be migrated to IP. And also when it goes towards the transmitters, Rive is currently thinking about an interesting use case in my eyes, where they want to monitor transmitters with simple IoT sensors across 4 and 5G connectivity, because not every transmitter has an online connection. So project is done, but as I say, never finished. It constantly evolves, it moves on. What did we learn? Really the lessons learned in this 1-year project we have done. We have all those, we call it enabling technologies. It's software. We do things in software. We have many, many options. When you talk to the customer, when you've seen those visual overviews, the logic, there are thousands of ways how you can deploy such project. The base layer technology, this was easy. It was 2022-6, 2110 and compressed. But how to use the visual overviews, what kind of operator panel do you want to have? They started with classic button panels, source destination, hardware panels. Turned out doesn't work because it's so dynamic they didn't want to reprogram. So we ended up having those list views. They don't know what's next. You don't really know what are you doing the next 2 to 3 years. Will we use IoT sensors for the transmitters? Will it be something completely different? The only way it turned out, we need to turn this into a very agile project. It was a classic RFP, a couple of hundred pages. You have to answer, hit every tick box. But at the end, when you look at it after 1 year, it's a different project, to be honest. And the only way to really manage that, to handle that, we say, is in a DevOps style, in a very agile style, together with the customer. Not only the customer, but also with Skyline, obviously, as us, and all tech partners involved, together with the system integrator. Only then we could make this work. A couple of things we learned, quite obvious probably, but still worth to mention. Different vendors, different brands, they behave differently. Cisco, Arista, they have pretty much the same functionality, but it's not the same. There are switches out when you reboot them. You have to reapply the static multicasts. Others, they just keep it in memory. So when you do plant maintenance, when there is a power failure, the layer on top data miner needs to manage things in quite a different way. Also, again, some learning. Customer cannot wait for products to be finished and ready. This is not the case anymore today. You constantly need to change, you evolve. a lot of products are buggy or have missing features. It takes a while. There is no way that you say, I wait for another 3-4 months, then it's done, then we have a guarantee, everything is up and running. No, you need to find a way. Again, that's all about agility, to say we need to deal with those products. We have to partially implement it, we have to find a way to work around something. Otherwise, this will not fly, or we would have delayed that project for a couple of years. And most important in my eyes, also what customer agreed and found out afterwards, a small lab system is not sufficient anymore. They heavily expanded their lab system over time. They started with a very small switch fabric, a little spine leaf network, but we could not simulate all their workflows. It was just impossible. And we had to invest together with the end customer in a large lab system to simulate and test each and every workflow you deploy. When you work agile, when you do a lot of changes, you can't do this on the production system. Simple example, if we would introduce a bug or something wrong in LLDP or the network topology detection, that has an immediate impact because it's all automated on the SDN control layer, and it would bring down hundreds of channels when something goes wrong. So we have to test really each and every potential workflow, every setting, every change we do together with the vendors in that lab system. Otherwise, we would build that project, then it would be a pretty static one, and nobody would ever be able to touch it again because people would be much afraid to do any change because it could break things. The only way is to have that lab system in place. And I want to thank you very much for that.
Thomas, thank you very much. And we'll see you again soon.